A palindrome is a non-negative integer number that reads the same forwards and backwards when written in base 10 with no leading zeros. A 6-digit palindrome n is chosen uniformly and at random. What is the probability that n divided by 11 is also a palindrome? Now consider a palindrome, 6-digit palindrome, ABCCBA, where the letters denote digits, and using our divisibility check for 11, alternatingly adding and subtracting, we find that the resultant is 0, which is congruent to 0 mod 11. This should be an equals 0, which is a multiple of 11, which makes this divisible by 11. So we don't have to worry about the case where n is not divisible by 11, because this cannot happen. Now, it's easier to, rather than thinking about what happens when we divide a palindrome by 11, and if we get another palindrome, it's easier to go backwards. Like, consider a palindrome ABBA, like in the 4-digit case. This is case 1, the 4-digit case. If we multiply this by 11, can we get a 6-digit palindrome? Now, the problem with doing this is even in the largest palindrome, 9999, if you multiply this by 11, the units digit is 9. But that would force the leftmost digit in the 6-digit palindrome to be 9 if we wanted it to be a palindrome. But this is clearly not obtainable when multiplying a 4-digit by 11, because this is just too vast to obtain. So we're stuck with 5 digits since 4 digits don't work. So consider ABCBA. We can 5-digit. We can multiply this by 11 and see what we get. ABCBA times 11. Let's see. ABCBA, ABCBA, and what we get, A plus B. This isn't quite in alignment, but just to give me space, C plus B, B plus A, and A. So these are the digits of our new 6-digit palindrome. Now the problem is we know that this is a palindrome. If none of them carry, then clearly the digits are the same by commutativity of addition. But what if one of these carried? If A plus B carries, then A becomes A plus 1. But A over here remains A regardless of whether B plus A carries. So what we conclude, and you can see a similar thing with B plus C. If B plus C carries, then A plus B becomes A plus B plus 1, which is different from B plus A here, which cannot be B plus A plus 1 since A is a digit. It cannot carry. So what we've concluded is this works for all 5-digit palindromes, n over 11 as a 5-digit palindrome. It works for all 5-digit palindromes that when multiplied by 11 don't carry. So in effect, we are now computing the number of triples A, B, and C. So this is now a counting problem such that A plus B is less than 10, or this is just another way of stating the fact that it can't carry. And this is a fairly easy thing to count. Now we can just do this directly. A has 9 choices, B has 10 choices, 9 choices, B, so A 9 choices, B 10, and so in total, AB has 90 possibilities. And if you just do casework on B, if we did B equals 1, and I should mention A has 9 possibilities because it cannot be 0, right? If this was 0, then it would reduce to a 4-digit number, which, and we've said, it went with no leading zeros as well. So A cannot be 0. So if you count this and just add up all the cases, which is really straightforward, like if for this case A has 8 choices, B has 9 choices, since A is less than 9 and B is less than 9. If you add these, you get 330 divided by the total number of such palindromes, which is 900, and that gives you 11 over 30. And 900 because we have 9 choices for the first and 10 for the second two.